All right. Hugo, how you doing?
Hey, I'm doing good. Well, thanks. How are
Great.
you?
Absolutely fantastic. Nice to meet you.
Nice to meet you too. Nice to meet you too. Good to
Yes.
see the Blockathon video going on.
Yeah, absolutely. It's been going pretty well. We've got over 10 teams who've signed up over the last week and are currently hacking. A few really cool projects. There's one particular project focusing on completely remodeling the Great Barrier Reef. It's really cool. They're creating a full virtual metaverse experience for people to be able to experience the Great Barrier Reef for like educational and also fundraising purposes for conservation. So there's a bunch of other projects. It's really cool. We've obviously got a few people on right now. Let's probably wait a few more minutes and then we'll get started.
All right. Is it clear to see the slides in this format?
I can see the slides. That's all good. I'm guessing you're based in France, yeah?
Sorry?
You're based in France?
I'm based in Brussels. In
Brussels.
Belgium.
Oh, cool. Oh, okay, cool. Do you have a LinkedIn? I was like, there's a Hugo Heater from Brussels on LinkedIn, but I didn't know if it was you, so I wasn't tagging you in anything. But it must be you, Hugo Heater from Brussels. Like, how many of them are there?
I should update it a bit.
Nah, it's all good.
It hasn't been updated for 2 years.
I mean, look, the reality is that LinkedIn's for boomers, so, I don't know why I still use it, I'm borderline Gen Z, so.
Yeah, since Microsoft bought it and turned it into a kind of Facebook for work, it's becoming.
Yeah, it's interesting. Like the algorithm like pumps, but let me just. I'll give a few more minutes, and then we'll just get started. Usually, what happens is that people like continue to join as the call continues. So, I'm just gonna just send a. Okay. If it's all good, I think we'll probably get started. How's that sound, Hugo?
Sounds good. Give me just a few seconds.
Yep.
I finish.
No problem.
All right.
Great.
So let's get started.
Sure. I'll do a brief intro just for everyone. Thanks everyone for coming to our second workshop for the Metaverse Blockathon. We're super excited to have Hugo Heater from Aleph, who'll be doing a talk on virtual machines and resilient and decentralized backend for your Web3 projects. So super glad to have Hugo on board. My name is Paul Penendis, and I am a core contributor for Blockathon DAO and running operations, community operations for the Metaverse Blockathon. So thank you all for coming, and I'm super great to have you all, and I would like to hand it over to Hugo, who will start his talk.
Hello everyone, and thanks for the introduction. I'm really happy to be on this, to give the workshop with Blockathon DAO. Thanks for welcoming me. So in this workshop, I'll be talking about how to build resilient and decentralized backend for your Web3 projects using Aleph virtual machines. So I'll start with a short introduction to Aleph, then I'll introduce you to the Aleph APIs and the core concepts of Aleph. Then I'll go into understanding a bit more how the virtual machines work. And then we'll really get our hands on and create and run a simple Python program on the Aleph virtual machines. So if you want to participate hands-on, these are the requirements you will need. If you can also just watch, but if you really want to participate, you will need a recent version of Python and pip, the Python package installer, preferably on Debian and Ubuntu. That's what we are using, but anything else is fine. And if you're using another operating system, you can also use containers or virtual machines. So you can use Docker on Windows or on Mac, for example. That works fine. You will need a library for elliptic curves. That's what we use to sign the messages in Aleph. That's what's used by Ethereum. So it's one of the cryptographic algorithms we're using. Again, it's available on Debian, Ubuntu, and many other operating systems. And to go all the way, you will need SquashFS user space tools for archiving programs and volumes. That's optional, you don't have to use it, but if you want to use volume, then you have to use SquashFS, which is a kind of zip program. It compresses data in a way that can be used very easily on Linux. And these are the commands you can use on Linux to install all of this. I'll get back to this when we get on the hands-on. So, a bit more about Aleph. So we have the Aleph is structured in this way. We have the application layer. This is where you have apps that do things on Aleph. Where you're running, for example, web apps. We have a Dropbox blog as a demo. We have a blogging app on our website. These are all using Aleph, and they're basically web apps running in the browser in this case, but it could also be native apps on mobile, native apps on desktop, server apps. Then we have our SDK layer. We have a JavaScript and a Python client libraries to make it easier to use Aleph. But it's still just HTTP calls and WebSocket calls under the hood, so you can always just attack the APIs in whatever language you like without using the SDKs. It just makes it a bit easier also for the cryptographic tools. Then we have the Aleph off-chain peer-to-peer network layer. This is basically, we have the Aleph nodes, which are a collection of servers. There are about 80 of them at the moment. They're all talking to each other and exchanging the messages on a peer-to-peer way. So when you publish data on Aleph, it will be propagated through the network along these nodes. And that gives us an off-chain. Storage is cheap. It's not as expensive as storing it on-chain, where every byte counts. Here you can just store much more. And it's much more flexible in terms of requests you can do. So that's our peer-to-peer network layer. Powered by Aleph nodes. And then we have cross-chain connectivity. So messages are regularly archived. They're like packed in a big archive, and this archive is pinned on IPFS, and the IPFS hash, the unique hash for this archive is published on-chain, which means that there is no way you can fake the data published, and you can also always get it without accessing the Aleph databases. just via IPFS and this hash on-chain. So we have some interesting guarantees there that the message has been published and you can really rely on it because there is proof on-chain that this message has been published at a certain date. And you don't need to query the Aleph database if you want to get if you want to get a big bunch of data from Aleph. For example, when we start a new node, and it's a decentralized network, so everyone can start a new node. When a new node starts, it will fetch most of its data directly from this on-chain pins. And that way it will fetch most of the data from Aleph, and just the remaining is to catch up is catched on a peer-to-peer way. The data structure, so the Aleph is mostly at its core, we have a database of messages, and each message has a type. There are a few different types that we'll go through. The content, and this content is either something custom, whatever you like, or if for certain types of messages, then the content has to follow some specifications. We'll see this when we create a program. For example, a program is a certain type of message with constraints on the content to be compatible with the VMs. The item hash is the unique identifier of the message, and it's also a hash of the content that we saw just above. And this hash is also signed, which means you cannot forge it. Nodes cannot play with the content of messages. We have the sender, that's the public key of the sender, and we have the chain. And the chain is basically matching the sender, so different chains use different kinds of encryption, cryptographic keys, and that matches that explains what kind of key we're using. For example, if we're using Ethereum, it's some kind of elliptic curve, but some other chains use different curves or different algorithms or different formats for the addresses. So that goes to specify which format the public key is using. And we have channels, and the channels allow you to use like a namespace. If you're creating an app, and you put all of the messages from your app inside one channel, it makes it much easier to search through, to explore, to manage. There are a few more. I'll not go into the details of everything, but these are really the most important fields of the Aleph message. So there are a few message types, and these are the 5 message types supported at the moment. There is the post message type, which means just post whatever content you'd like into a message in the database. We have store, and store is interesting because it's basically saying I have this binary data, this file I want to store, and you can store it either directly, if it's small, inside the Aleph database, or if it's bigger, you can use IPFS, and you can just tell Aleph, hey, I want you to pin this file, so it will persist, because in IPFS you can add a file to IPFS, but it will not persist if all the nodes storing it disappear. So by sending a store message, you can tell Aleph, hey, store this file forever, or as long as I want to store it. And Aleph will take care of this. You have the aggregate messages, which are, so aggregate is a kind of key value store. So you send new messages that update the keys. And when you do queries on the API, it will give you an aggregate of all the keys. So you can easily manage a bunch of variables that are changing, user settings, some user data using this functionality. Then we have program, which allows you to register a custom program to run inside a virtual machine. And we have forget messages, which allow you to remove data content from the database and from the storage. Now, if you, so this will remove it from the database, but as I told you before, the messages themselves are archived, and it will not remove it from the archives, because that's not possible. However, it will remove the content from the database, so it will not be available by querying the nodes. And if you have data pinned on IPFS, it will stop pinning it and remove it. So all data that's an attachment that's stored, linked to a message, will be deleted. Now, if you want to create a DApp and use Aleph with it, this is the typical architecture you would have. So we have at the core here a web browser. This can be, as I said, a native app, another kind of app. And on the bottom left, we have the Aleph core channel nodes, which manage the message database. So here we have, for example, a post message, the aggregates, the store messages. And they can just read write through them through an HTTP API. And we have load balancers to make sure that you always reach an available node. And the fact that we have 80 nodes, it's abstracted from the user. On the top left, we have Ipfs Connectivity. So if you want to add a file on Ipfs, you can very well run an Ipfs client inside your browser that will serve the file on Ipfs. And then you send a store message to the Aleph nodes to say, hey, I want to pin this content. This is the CID, the content ID, store it, and the nodes will use Ipfs, find your browser through the peer-to-peer network of Ipfs, and get the data from it. And once it's stored on Aleph, you can just remove it from your browser if you want. On the top right, we have integration with wallets. So you can use MetaMask or other wallets in your browser, interfaces with hardware wallets if you want to sign your messages. This is very important because the Aleph system is mostly public and open source. So, and everyone can run a node. So you don't want to trust the Aleph nodes too much. So you should sign all of the messages, and you have basically to sign every message you publish on Aleph. And you can also use encryption and decryption to encrypt the files. So even if they are publicly available, everything you publish on Aleph is public. But if it's encrypted, it's not really public anymore. So you can use the wallet integrations for encryption and decryption, or use custom JavaScript code, custom code in your client as well. And then we have on the bottom right the compute resource nodes, and these are special kind of nodes on Aleph that run the virtual machines, which means that you can use whatever kind of request to run. To talk to whatever code you like inside a virtual machine. Typical uses at the moment are to index and cache data. We're working on indexing different blockchains. That's a different topic on Aleph, and we're working on it with Aleph virtual machines. Some people use it to make dynamic NFTs. So you have a different URL for each NFT, and the virtual machine is generating the NFT depending on the path in the URL. So you can have NFTs that are different for each small URL, but you only store one program. You can have NFTs that change over time, things like this. You can use it for webhooks to interact with the rest of the internet from a server. And you can also use it for custom software, custom databases if you want to use other common databases other than the Aleph database. You can basically do whatever you like inside these virtual machines, and that's what we'll get started with today. If there is any question, don't hesitate to interrupt or to send a message in the chat. Now, if we want to publish some messages on Aleph, we have development kits in Python and JavaScript. These are the two main languages we're supporting at the moment. And we plan to add support for more. But anyway, you have also an HTTP API, so you can just use Aleph from any language you like. And you will find here some links to the documentation in JavaScript and Python. If you want to start using the Python CLI, the Python library, so we have a Python library, but also a CLI in Python that you can start using very easily. So to install it, you just need to do pip install aleph-client. And these are the options that you can use. So I'll just go back to the first slide to further requirements instead you don't have them. So you can start playing with publishing messages in Aleph. So the important things are this library here, which cannot be installed via pip. and then the Aleph client here. I hope it's okay for everyone. So I'll just do a small demo. So here I have the transition. So here I have just a terminal with the Aleph client installed, and I can just type Aleph -help and see. Yes, of course, the slides will be available afterwards. And we can, for example, just post a message. So if I want to post a message, I can just do Aleph post. And I can post a message, for example, hello. So this is JSON. This has to be JSON upload. Turn DAO. Control Z. And I now have a copy of the message I just published on Aleph. And I can look at it if I go if I open my browser on the Aleph Explorer. So this is just a small web app that shows everything going on Aleph. And I can see here my message, the message I just published. I'll click on it, and I can see here a copy of everything with information about the sender. And you can see here the address, the time, the content of the message, and the type of the message is by default a text. You can use, this is how easy it is to just publish data on Aleph. There are a few more things. You can see here Aleph pin that allows you to pin an IPFS hash. Aleph uploads, so you can upload a file. For example, well, here I have just a few files from the source code of the Aleph client, but I can do Aleph uploads the requirements, for example. And they were just uploaded here, and I can see them. I should see them in the Explorer if I go back to the main dashboard. Here I have the file, and here I have the item hash. This is not an IPFS hash, this is a hash that's stored internally inside our database. So just to do this, I just use the command Aleph upload requirements.txt. So this is our CLI. We're planning to improve it and to make many improvements on the CLI as well, but you already have access to most of the functions of Aleph from the CLI, and else you can just use it as a library in Python. The JavaScript library does something very similar as well, and has some more functionalities. For example, all the encryption is supported by and the MetaMask connections are supported by the JavaScript library. So this was our practice for the small demo. So don't hesitate to play with it. We have the documentation on Gitbook. We have we're really active on Telegram. Don't hesitate to play with this. Now let's get a bit deeper into the part of today's workshop, the virtual machines. So, small introduction. So, Aleph is using something called fast micro VMs. And the idea here is that we want virtual machines that run very quickly. We want the program to run in less than half a second. And to do this, we're using something called Firecracker, which is an open source project to run virtual machines. That only run Linux on Linux, but they strip a lot of stuff. If you're used to virtual machines like VirtualBox or Parallels or other technologies on your desktop, these will emulate USB ports, they will emulate the GPU, a display, a lot of things. In these virtual machines, they stripped a lot of this to make it run really fast, but there's no notion of what USB is because it's not relevant inside the VM. There's no notion of what a screen is and things like this. But that makes them really, really fast. In half a second, we're around 400 milliseconds at the moment for the complete starting a whole program from zero to having the response. And we're planning to we're hoping to strip that to maybe 250 milliseconds, something similar. It's using a hardware acceleration using Linux KVM, and it supports Intel CPUs.
There we go.
Hey,
Don't know what happened.
Okay.
Yeah, we're good now.
Was something missed?
Only you only muted for like 20 seconds. So you basically you went through. You know, you would like to eventually get down to 250 milliseconds. That part, I think, that's the last time. So not very much.
Okay, right.
Yeah.
So they run very quickly, and then I was speaking about the CPU support. So it supports Intel CPUs, and AMD and ARM are in development preview. They're working really well from our experience. The only issue is, of course, when you're using ARM, it's a different architecture, so you need to change the tools you're using. But it's working very well as well. Here's the global architecture of the Aleph VM components. So we're really going back to understanding how they technically work here. So we have the kernel in the bottom right here. This is a Linux kernel that's optimized to run in these VMs, so which has a lot of things disabled to also run fast. We have the runtime. The runtime is here. And that's a customized Linux root file system. So we have made a few changes to normal Linux distributions to run and to integrate with the rest of the system. Then we have the code archive. So that's the user program that's running. And these are stored separately, so you don't have to store a whole root file system for every program. So these are on the file system here. We have your code, the runtime, so the root file system, which is mounted read-only. And these are available inside the VM where your user process is running. Around this is the jailer. And the jailer is something a bit similar to Docker. It's using Linux namespaces, and it's making sure that the host is very secure against the VM. So even if some program gets outside of a VM, it's still inside the jailer. So it's really hard for one VM to disturb another VM running on the same computer. And the user process is talking with the VM supervisor that's in charge of launching, stopping the VMs, using a specific type of sockets called vsock that's specific to virtual machines. On top, we have a reverse proxy for HTTPS. And on the left, you see that we have internet connectivity. So this is an option that you can enable or disable when you when you upload a program on Aleph. You can give it internet connectivity or not. And that's an option. So in some cases, for security, you might not want to give any internet connectivity to the VM and only access Aleph APIs, for example, and the client connections. At the moment, Aleph VMs are triggered by HTTP calls. So we're working on adding long-running VMs, but at the moment, the main way of using VMs is called Lambda way, or software with our function. So you have a client that's querying an HTTP, the VM from an HTTP request, and the supervisor will launch the VM on demand, execute all the program, and then if no more requests come in a short duration, you will just stop the VM so it can start again on demand. And you can see here the VMs accessing the Aleph network. The runtime load. So the runtime is a Linux root file system configured to run programs on Aleph. It is basically based on Debian 11, at least our official version that we provide. It's based on Debian 11, but everyone can create their own runtime. Aleph is decentralized at the core, and we want everything to be decentralized. So the runtime is also something that you can build your own. You can just customize the one you are using. The script that builds this runtime is open source. It's on our GitHub repository. And the main change is the init system. So we replace the init system that's basically the program launch at boot to launch the other programs, but one that would just directly launch your program. And there are two interfaces supported. One is called ASGI, something specific to Python that allows you to launch Python code for using web frameworks, and it's supported by most Python web frameworks such as Django, FastAPI, many other new frameworks that work asynchronously support ASGI natively. And if you're not using an ASGI compatible Python code or Python framework, or if you're using any other language, we're running on Linux here. You can use whatever language you want. We have demos using Rust and Go and JavaScript, for example. You can just listen on port 8080 on HTTP, and the init will forward your request to that port, so you can just run any web software you like. Then the next thing is the entry point. So that is the next notion you need when you're specifying, when you're creating your program for Aleph. And the entry point is just specifying how is your program called. So the program will be called via its entry point. If you're using ASGI, then that's the Python ASGI entry point, which takes the form of the name of the Python file, semicolon, and the name of the app variable inside the main file, basically. And if you're using Python, you also have the Aleph client, so the Python library to interact with Aleph that's available and already pre-configured to work out of the box. So it's very fast to launch Python code from our runtimes. If you're using the HTTP server way, you can run processes in any language. So you just have to listen to requests in port 8080. If you want to access the guest API or other functionalities, you need to open a specific kind of socket called vsock and talk over that socket. It's available in many languages, but not in every language. So you have to see if you want to access advanced features provided by the host. You may need this if you're just talking on the web, talking on the internet, using pure HTTP APIs from public nodes. Then you don't really need this. It's just for advanced functionalities. The next notion is the volumes. So the volumes are a way to extend your virtual machines. So you can create new volumes that will be mounted on the system. It's a bit like virtual USB keys or virtual CDs. CDs sound so old, I should use this. So we have 4 different kinds of volumes you can use inside the virtual machines. You have the read-only volumes. These are useful to separate your Python, to separate your Python virtual environment. So all the libraries of your project, you can put them in a separate volume. Then your code, so you can update one without updating the other. That makes it easier to not update everything every time. Also makes it lighter in terms of storage. Same thing for JavaScript. If you're using JavaScript, you have this very big folder called node modules. You can just put it in a read-only volume and mount it separately. All kind of static data should also be ideally in a separate volume. We did a workshop in the Paris peer-to-peer conference a few weeks ago, and we were doing machine learning inside Aleph VMs, and we had about 1 gigabyte of trained machine learning models. So we used a read-only volume to access these. And since anyone can use everyone's volume, if you know the hash, it also means that we could provide and store this 1 gigabyte of data, and everyone could just reuse it without uploading it themselves. And so these volumes can be updated independently from the program and the runtime and maintained by a third party. So you can also decide to depend on third parties to work with to provide some data, and you're providing a program on top of it. So that allows you to have some collaboration. They're maintaining the data, the machine learning models, the Python library, something else, and you're managing the program, and you can just work together. So the second kind is the host persistent volumes. So these are volumes persisted on the VM execution node, so the core, the compute resource node, and it allows you to store data on it, but they may be garbage collected by the node without warning if it's lacking space, because the compute resource nodes are optimized for computing, not for storing a lot of data. So if your program is not running for a while, then they may just delete your volume if it's taking too much space. We have the ephemeral volumes. So these provide temporary disk storage to a VM during its execution without requiring more memory. So if you want, you just need a little bit of RAM, of memory, but you need to temporarily store a lot of data to process it, and you don't really care about getting rid of it just after the VM stops. For example, you're indexing some data, so you just store everything on disk, and when you have your all of your data, you just go through it, parse it, get your result, and then you can just delete this ephemeral volume. And then we have this work, it's work in progress, so we have the store persistent volumes. So these are volumes that are persisted on the Aleph network. So when you have a VM, it will always try to use the latest version of this volume. And this means that you can store, for example, your WordPress database on this. And it will stay available even if the VM stops and the core, the execution node, the server it's running on, is shut down. Your program, your website will just move to another node, to another server, and you will get all the recent data available. So with all these new concepts, the architecture gets a little bit more complicated. And this is the updated schema that we have. So we still have the user process here, the Linux kernel. Then we have here a mutable volume an immutable volume here that's read-only, the runtime, the code. So these are all volumes that are mounted inside the VM. We have here the init system that's launching and communicating with the supervisor here. We still have the internet connection. Then we have vSoc connection that allows you to talk with the guest API. So every VM that runs has access to some features from the host through this guest API that gives it more functionalities. For example, there is a shared cache, so if you just need to store a few dynamic variables, a counter or something like this, you don't especially need to create a whole volume like partition disk for this. You can just store them inside this key value store that's local to the server. So if you want a like global key value store, you should use Aleph Aggregate Messages, but if you just need something local to the VM, you can have this local key value store. And this is also taking care of talking with the Aleph network in a secure way. So coming soon and in development, we have the use of secrets inside virtual machines. And this is a hard work because at the moment, so everyone can run a compute resource node. The only thing you need to host virtual machines is you need to be supported by someone who is running core channel nodes of Aleph. So we have about 80 core channel nodes, and they all have up to 3 compute resource nodes linked to them. And so anyone can run these compute resource nodes, but also all the data on Aleph is publicly available. So we're working on using very CPU technologies to allow you to use secrets inside your virtual machine without the operator, the sysadmin of the server having access to it. And this will allow you to store credentials, authentication tokens, keys, and so on inside the VM and to make them available inside your VM. So you can do things, for example, post to Twitter or manage chains, keys for posting things on chain, authentication tokens, and so on. You will be able to use these inside virtual machines. And the second thing is long-running virtual machines. So for many use cases, this Lambda mode to react on a request is very handy because it's very reliable and it's also very cheap. It just uses the server for the time it's running. But some use cases need virtual machines that keep running all the time. For example, if you want to run some blockchains have WebSocket APIs. So if you are indexing blockchains, you may want to use these WebSocket connections instead of HTTP calls from the server, or instead of running every few minutes and pulling the changes. And in that case, you need something that keeps running. If you want to run a game server, like a Minecraft server or something, you also need a long-running virtual machine, and not something that just reacts to HTTP requests. So we're working on adding these soon. Let's see how to run a Python program on Aleph. So we made a tutorial to go to this, and I'll just open it and I will copy the link in the chat here. Here. So if we go through this, we'll go through all the steps with the requirements again to create a program, a virtual machine, upload your program on Aleph inside a VM. So you have the requirements, then understanding the VMs, more details about what I talked about. How to write a Python program, how to test it locally, and then how you can upload it, run it, and at the end, just run it on the web. So for example, here I have a program that's running on Aleph, and I can just run it from one of our servers, and we have the result here. This is JSON data that was returned by this program. So I encourage you to now go through this tutorial, and if you have any questions, just come back to me, and I will try to help you with this. So you can go at your own speed, and don't hesitate to post about the issues you face or the new ideas you would have about it.
Cool. Is that the end of the talk?
This is the end of the talk part, and now it's the really hands-on part. Yes.
Sure. Are you continuing on to the next part, or?
Sorry.
Are you continuing on to the next part, or is that the end of the talk? Because obviously we've got Q&A.
Yeah, just after this, so
sure.
I have just a slide for Q&A, but
oh, okay.
So to just a discussion. So if you want to discuss, we're mostly on Telegram. You can join the Aleph developers room. I'll also copy the link here in the chat. And these are the nickname of the two developers that are. So that's me first, and then that's also the other developer is working the most on the back end and on all the SDKs. So if we can also do Q&A while people are experimenting, I think it's good to just mix the two together. And,
Sure. One thing I'd like to add is that this talk is being currently recorded and will be posted on YouTube. So for people who are in this call who are trying to keep up but maybe couldn't have, you can actually go rewatch it, right? Because there's so much information here about the entire stack, the entire Aleph stack, and all the information describing it all, not only with the tutorial that Hugo provided. So I'll be posting that link very soon, and of course the links that Hugo's just posted in the chat I will also post in the YouTube, which is really great. So thanks, Hugo. So I would like to provide an opportunity for anyone in this room to ask any questions or have any comments before I ask my own. Mike, you were saying you find this quite interesting. Does this, what Hugo presented, does it have any relevance to kind of your project you have at the moment, or kind of your previous experience with what you currently do? He might not be here. So good. I have a few questions. So Hugo, you were mentioning how currently you guys don't manage basically secrets like private keys and other other kind of methods of authentication on your VM. How do users currently use Aleph if they want to kind of like send a tweet, or they want to sign a transaction, etc.? Like, how do they interface with Aleph in order to get that done by the VMs?
So there are two ways at the moment, but usually, so since secrets are not safe inside VM, we know that some users still do use it. They use the key value store inside the VMs because these values are only accessible to the operator. So if you're running your own compute resource node, or if you're running your VM on one of the Aleph compute resource nodes and you trust Aleph not to mess with it, we know some users are doing this. I mean, that's fine, but the idea is to be decentralized and to not trust anyone.
Of course.
Not have any weak links. So we know some users are doing this. We know some users have their own software that's running apart from Aleph, so they run all of the logic on Aleph. And then when they need to post it to do something that requires authentication, then they have a piece of software that's running somewhere else that's handling this part. Also, some people have hardware, not hardware wallets, but hardware wallets or similar. How is it called? Like when you have like YubiKeys or HSM, hardware security modules.
Sure.
Don't work on the compute resource nodes. At least you don't have any available on the current compute resource nodes. So in that case, so cool, their server that has the hardware security module. That's doing signing or the decryption. That
makes sense. And when Aleph is saying how they're going to start introducing this capability for secrets to be a part of the VM, how does that happen? So for example, you're just saying how you got like a hardware compute resource and you're using a YubiKey. In that particular scenario, like that's a specific hardware requirement that needs to interface with the VM, and in doing that in a decentralized way, that'd be quite difficult, wouldn't it? Because like, wouldn't Aleph need to have its own hardware components? Because like, you know what I mean?
Yeah. So what we're looking into is features of the CPUs designed from Intel, from AMD, from ARM makers. That provides trusted execution zones. So it's the CPU makers that design the CPUs to have some functionalities that allow encrypted computation that's not available to the sysadmin. So we're investigating these features. Intel and AMD have different APIs, different functionalities, different features. So we're still investigating which one would work the best with Aleph, with our constraint, with our architecture. But the idea is to rely on these. So that so it doesn't require plugging in something into the server. Also have considerations like the availability of these features. It's quite widely available on Intel. but on AMD it's mostly on server and CPU, so we need to keep the servers affordable for operators. So we have a lot of questioning like this.
Right.
But the idea is really to use these trusted execution systems made by the CPU designers.
Right, gotcha. So you got basically the security enclaves in these CPUs that you can get access to, and you guys are in the process of basically incorporating that into the VMs that Aleph provides. That makes sense.
Exactly.
Yeah, it makes sense. So I do know that Aleph has the capability of working across multiple blockchains, and also a lot of dApps on Solana use Aleph. Would you be willing to describe a little bit more about some of the blockchains that Aleph has been interfacing with, and in particular maybe describe the widespread use of Solana dApps for indexing using Aleph? I think it would be really great to have an overview of the current adoption of Aleph and where you think potentially it can expand to in the future.
So Aleph interacts in multiple levels with blockchains. If I go back to the I think I have. Oh, no, I didn't include this slide. So if we look at Aleph, there are basically different ways to interact with the blockchains. One way is to support the addresses from the chain. So a user that has an address on a blockchain can also use this same address to publish messages off-chain on Aleph. And use this same address key to decrypt data, so people can exchange data by encrypting them towards each other, stuff like this. So that's the message level support. We have, as I said, the messages are archived in blockchains. So at the moment we mostly archive it on Ethereum. We used to do it on some other chains, and we're working on adding more modern chains for that. So that's the archiving part. And then there is the indexing. So we're mostly working on indexing Solana at the moment. And so that's the index part. We have some feature we would like to do is, for example, launch a VM, launch your program when something happens on one of the chains, on one of the addresses you're interested in, or one of the smart contracts you're interested in on a chain. It will automatically trigger your program inside an Aleph VM, for example.
Gotcha.
So these are some of the levels with which we are interacting with the different blockchains. And they all have different levels of support and constraints. I'm not the best person to talk to you about all the details about the indexing because I have colleagues that would do that much better. So for the indexing, our goal is also to, the indexing is very heavy, right? So especially when you're working with things like Solana with very high throughput. Yep. So we're also leveraging the virtual machines to work in a decentralized way to decentralize all that load across many servers.
Gotcha. Yeah, makes sense. Cool. Does Aleph plan to kind of, I guess it kind of depends on the demands, but Aleph, I guess, plans to connect with every major blockchain, right? Because it makes sense for it to do so. I guess pertinent and dependent on the demand of particular users on blockchains to use decentralized storage and hosting, right? That makes sense. Cool. That's all the questions that I have in particular. It's really great to see, basically pretty much almost a full stack decentralized suite of solutions that, potentially dApp developers can have. So rather than only just building a dApp on top of a blockchain, now they've got middleware that they can use to actually, provide all the other services that's required to make a dApp function. So it's really great that Aleph's doing this. And we really hope that, with what Aleph's providing, we can have a full decentralization process rather than, relying on like Amazon, etc. all the time. I guess another question that I have, and this, I don't know if this quite makes sense, but of course, there's a lot of people who run nodes of particular blockchains on Amazon Web Services, etc. And it's quite a huge issue with regards to centralization, because ideally we have tens of thousands, 100,000, millions of people who host a node on their own server to really to really enhance the centralization. Do people use Aleph to host nodes?
Sorry, do people use Aleph for?
To host nodes? Like for like Ethereum, etc.?
So at the moment, to host nodes for blockchain nodes, you mean, right?
Yeah.
So at the moment, the fact that we only support this Lambda mode doesn't make it trivial. You cannot open ports, for example, yet.
Right.
So it's lacking some features if you wanted to run a blockchain node inside Aleph.
Gotcha.
With a permanent run VMs, that should be an option. I'm not sure if that would be the most economic or the most pragmatic way to run it.
Sure.
Because, many of the features that Aleph provides are not needed when you're just running a blockchain node.
Yeah, gotcha.
So could be possible. I'm not sure it will be the best way, because you might want to just, the idea is to run your own computer on the chain.
Sure.
Just running it inside Aleph
wouldn't make much sense.
I'm not sure if you're running a small chain, I think it would make sense.
Right.
If you're running very intensive, I think it might not be the best choice. You're usually looking at dedicated hardware for that, where the only thing running is your node.
Gotcha.
A question, something I was thinking about a bit related to that is, so we're waiting for Firecracker to add GPU support. We don't have GPU support yet, but that's something also we're looking forward to add for applications, both for mining or for machine learning, for example. It's very useful to have GPU access inside some nodes, and that's something we're looking forward to have. We know that it's work in progress, but we don't have any timeline on when it might be available. Sure.
Thank you for your answer. We're pretty much rounding up to the hour now. So if no one else has any more questions, I'll just give everyone a moment. We'll wrap up the call. Just give a moment. Okay, looks like no one has any more questions. Thank you once again, Hugo, for presenting your talk on virtual machines from Aleph. It was really informative, very comprehensive, which is absolutely fantastic. And I think even if people were paying attention, there's so much info in there, which is so great. They can just go on the YouTube, and also access your GitHub links if they want to, retry some of the examples that you provided, or just start to try. So, thank you so much, Hugo, for the talk, and I think we'll wrap up.
Thanks a lot for hosting this workshop.
No worries.
And thanks for all interesting questions.
Of course. Thank you. Have a good day.
Thanks.
No worries.
Have a good day, everyone. Bye.
Bye. Thank you.
Bye-bye.